cover everything. The first few things. So then I have few slides on our group current work. I can show you. Okay, so here, so what is meant by federated learning? So here you have mobile devices you have. So mobile phone or iPad or notebook. So you have here. So here, this data you have in your mobile phone. So now here in the federated learning, say here you have the edge server you have, or parameter server you have. So in federated learning, what is happening here, every device train their local model. Say, so that means here the weights are going to be adjusted using the local data. Then what will happen? Deliver the local model weight to the server here. So server, so take the weights W1, W2 up to from all devices, the server collect the weights of the local model. Then what it will do, the server, it is going to do the aggregate the local models and broadcast back to the local devices. So based on the broadcast one, they retrain again. So this process will continue for a certain number of iterations. So now the question is, why we need this federated learning is because to maintain the privacy. Because here the devices, they cannot share their private data with the server. So, but what they can do, they can train their model and they exchange only the model but not the data. So, the main purpose of this federated learning is to preserve the privacy. So that means the data are not shared with the edge server.
When you are saying they are going to share the model?
Only the model, not the data. So here they train the local model. So then the local weight they send to the global weights only will be sent. So then this one collect the weights from everything. So simple aggregation, federated aggregation, then they broadcast back to this one. So then they get new weights. So then based on that they will update again. So then they will send it back. So back and forth, then they finally converge to a common model for a certain common application. So now the problem here is, here we are going to have, in practice, we are going to have different heterogeneous, not the all devices won't be homogeneous requirement, because every device has the processing power different. So the storage facility is different. So all devices have different environment. So therefore, so we are going to have heterogeneous, but the fundamental model assume that all are homogeneous, identical. So then we exchange the local models. So here the data different, data set 1, data 2, data 3, data different, but common application, common model. So they exchange their weight, not the data. So here the learning objective here is, so minimize the loss function. So you know that in the neural network, so we learn, so minimize the loss function. So weight is going to be adjusted such that the loss function minimized here. So here the n, so here in this here, so here we have nk is the number of data elements in the kth device. So this is the percentage, n is the total number of data values. So here we are going to have this we are going to aggregate the functions with the weight of pk. Pk is the percentage for the kth device. So now here we are going to have the two types of global model updating. So one model is going to be, so here the first model, here the update is done is in the edge server. Second one, all local devices, they do the update in their local device and send the final weight to the global server. Then global server update their weight. So this global server update their weight. Whatever it got the weight from the local device. There are two ways they can update. One is, so that is the global server update the weight and exchange to the local devices, or local devices they train and they send the final weight to the global server. Either way, the update can be done. So now so here, say if you take these computer science papers in 2018 and 20, so here to improve the accuracy, so and the convergence performance in the global model, so here we have a weight here. So the weight means, so for the previous model weight, less weight is given. Here e to the power e over 2. Here the old times, the previous time you had some models. So for the previous time models, then we use the lower weight here. So that way we can improve the accuracy and convergence performance. So here the less weight used for the previous model, here e to the power minus this value. So when you take the previous time intervals, so here the low value of weight is used for the previously trained local models. So this is, then when you take inverse distance aggregation means, so here for some models the weight compared to the global weight, the significantly different. For those models, so here those weights we give high weightage, this pk we give high. So by that way global model is weightage of the weight of the global model is updated. So then the adaptation is done at the layer wise. So if you take neural networks, you have several layers you have. So when you have the layer wise aggregation, so the weights updated at the layer level, not the global level. So layer by layer aggregation is done. So the advantage of the layer wise aggregation, so it can minimize the distance between the global model and the local model easily, because each layer then we do the aggregation instead of everything together. So then, so here the problem is, so here we are going to have, in practice we are going to have heterogeneous network. So the devices are going to be the different features. So because of that, we are going to have two problems we are going to have. One is Klein drift. So the Klein drift is, so the global model and the user model after few iterations move away. So because of the heterogeneous devices. So to solve this Klein drift, so a stochastic averaging approach was proposed in this paper. These are the papers in computer science. So to solve this clay and drift, then to solve this lack of adaptivity means, so that means when you take the loss function, so over the time interval, the tail end weight will not decrease. The loss function after few iterations it should decrease, but it won't decrease. So that is called lack of adaptivity. For that, to solve that problem, so in 2020 they proposed so adaptive learning algorithm. So they have adaptive parameters, so such as adaptive learning rate. So they can adjust based on the statistical data they received. So here these are the adaptive algorithm, the available in the adaptive optimizer available in the previous literature. They utilized to update the federated learning update, to update the global model. These all are in computer science. So here there's another algorithm. So here they used in the computer science literature. So how to reduce the tail end fluctuation of the loss function? They use another way to update the weights using this approximation, using the when you have the large number of local models, we have the heterogeneous system. So in that case, we use for each device we have the adaptive weight. So by this way we can solve the second problem of lack of adaptivity. So then there's another algorithm also to reduce the tail end weightage convergence. To speed the convergence, they use another method in computer science. So the other thing is, I can leave this, I can go to the communication part. These are in the different algorithm in computer science. So then we go to the wireless network. So in wireless communication, so there are two approaches they use. One is digital approach, other one is the analog approach. So here in the analog approach, how the model aggregation is done, so they consider the energy efficiency and computation efficiency. So here in wireless communication, we mainly concentrate on communication because of the global server and the local models. So here if you take the wireless communication here, so here the wireless devices are there. So here this is the access point. So here the uplink and downlink. So here the local model weights up. So here the main thing is scheduling. So the scheduling is, so this base station is going to schedule these devices. So three ways it schedule. So that is random scheduling. So for first schedule for this equipment. So randomly select here. Then the second one is the round robin. So that is not random. It schedule for first certain number of devices, then another number of devices like that. So the third one is proportional fair. It is based on the certain criteria. So it select which device first, which one second, which one third. So the device how to select based on these criteria. So that is in the wireless communication, because we have communication constraint as well as computation constraint, because each devices have different computation facilities. So the next one, is the next one is the how the model updated here. So here each device has a local data set here. So here the local gradient is going to be updated. So then we have the scheduler. So it schedule how to get the gradients from each devices, then how to broadcast the global model to the local devices. So that is the scheduling scheme in the federated learning. So this is in the work of 2020. So then another one is model aggregation. So how to select the models optimally for aggregation purpose. So here the communication protocol should be designed. So that is from the device to the server. So that is how to select the clients. So that means we cannot take all the devices, we cannot take together. So we have to select the devices that would give the best effect to update the global model. So this works proposed in 2018. So then there are a few other methods they proposed here. Okay, so then here the different efficiency has to be considered. So here, because uplink downlink, so the communication resources are limited. So we have to consider, we have to optimize the transmission rate of each device. So we have to select the number of subcarriers for each device. So such that stochastic gradient descent can be updated from the local model to global model. So the constraint that we have to consider, the total energy consumption in the local device. So here K devices we have. So here we are going to have the energy constraint in each device. So we have to consider the energy efficiency and the communication efficiency. Those are some recent work in the optimization framework. Then some other works. Some other important work. So this is the some of the most recent work. So that is, say here we have different devices. So different devices, they update the weight and complete in different time intervals here. So this device, the computational facility is high, so it updates quickly. So some devices computation facility is very low, it takes long time to update the weight. So therefore, we will have to wait till the device 4 to update the weights to the global server. So by that way, so these devices are going to idle here. So because of that, to avoid that idle thing, so recently the asynchronous federated learning has been proposed. So it has been proposed because otherwise, so these devices will be idle for a certain period of time. So asynchronous federated learning means, so that means, say the first device finished here. So it is going to update the weights so such that these two devices cannot update, but these two devices can update. So by having this, instead of having the update at T2, if we have the update at T1, so these two devices no need to wait. So they can update and they can start their next update here. So next computation here. So these are some few other works in the literature. So now the wait. Right. So I can go to my work 1 second. Because as I did not expect to present this one, I did not select the appropriate slides and I did not prepare it. So that's what unnecessary slides also here. Can you? Because I did not select the all relevant needed slides. Okay. So basically, these are the work that we have done. So this, I am familiar with the work that I have done. So the previous works I presented in the computer science community and some wireless communication people about how to update the global model and the local model. So that is in the. So what we have done that is in the. So what we have done partial model aggregation and knowledge aided federated learning. So why we did in the federated learning, we have two problems we have. One is the limited communication resources, other one heterogeneity across the devices. Because say if you take the edge server and the local devices, so all these devices are going to use the same spectrum. So therefore, every devices, if they try to establish the connection with the edge server, so we may not be able to have the spectrum to transmit. So the bottleneck here is we have inadequate resources to exchange the training data between the local device to the parameter server or edge server. So that is one problem. Another problem here is we have heterogeneity. So the heterogeneity means, so that means the models, they do not have identical facilities, because some devices have high computation facilities. So the high storage facilities different. So therefore, each devices are not identical. So they, in the learning process, there will be unstable learning process, because the each devices are completely different from one another. So these are the two issues that we have. So here, if you take the communication perspective, in the literature, so mainly concentrated in these three areas. So one is resource allocation. So resource allocation is, say if you take some devices have GPU facilities, graphics process unit facilities. So how to allocate the workload for the devices with good computation facilities. So other resource allocation, communication resource allocation, so transmission scheme, so how many subcarriers allocated, those kind of things. Then bandwidth power allocation. So resource allocation is a communication perspective, one of the research topic in federated learning. Other one is device selection. So that means we cannot select all the devices to exchange the weight with the global server. So we have to maximize the scheduled device number. So we have to take as many as possible with the limited resources. So here, so therefore, the device selection is another topic. Then another one is model compression. So that is compress the model parameter, because if you have in a local device, if you have weights, say for example neural network, you have a weight matrix. So if you want to transmit the full weight matrix to the edge server to update, so you need enough communication resources. Because of that, compress the model parameters before transmission to the base station. So these are the recent works in last year and this year, 2000, most of the works 2021 and 22. So because this is a new topic, so most of the recent work in last 2 years, so most of the communication works on this resource allocation, device allocation and compression. So some other works in computation aspect. One is communication aspect, other one is computation aspect. So if you take the computation aspect, so here multitask learning. So other one is meta learning. Meta learning means learning about learning. So that is, so here meta learning, so different functions. So that means not one application. If you have many applications, so we are going to have meta learning for different application at the same time. So then some in computation purpose, model regularizations. So that means how we can improve the convergence stability. Some works in the optimal combination of global and local model. So these works are mainly in computer science community. So communication community, so the works in the communication aspects, this one. So here what we have done, so in our work, we consider the partial model aggregation. So partial model aggregation means if you take the neural network, there are many layers are there. So if you take the neural network's layers, so we can have lower layers and upper layers separately, because if you take the neural network, the the layers mainly used for feature extraction. Neural network upper layer mainly for pattern recognition. So if you take neural network, you have many layers. So the lower layer mainly feature extraction and the upper layer for pattern recognition. So now, so if you take the two types of layers, so here when we have multiple tasks or multiple learning, so we are going to share the common features we are going to share. Say if you have many devices together, we are going to share it. So we are going to share only the common feature extraction, because if you take the upper layer, pattern recognition is a specific one. So this lower layer is common for all devices. Upper layer is device specific. So that's what we don't need to exchange all layers. All layers means the neural network full model, it is not necessary to transfer. So that's what, by that way we can reduce the communication overhead, because from one model neural network, if you have several layers, so always if you want to transmit huge amount of data, you have to transmit to the edge server. So because of that, what we are going to do, we are going to aggregate only the partial layers. So that is, we are going to aggregate only the lower layers, we are going to aggregate. So by that way, so we can cope with the limited communication resources. So here we jointly optimize the computation and communication. So here if you take here, so you have k devices. So each device have a local data set, this number of data set. So all devices have total data set D. So here we have the feature extracted layer. So that is the lower layer here. So, here, here what we are going to have, we are going to have these 4 steps we are going to have. One is feature extracted. So that means, as I mentioned earlier, so from the local model, we are going to extract only the feature part. So that is, we are going to select the feature extraction, not the upper layer. So once we extract the lower layer, so then we are going to, from the global features will be updated by the, so in the local device, only update the local model of the lower layers, so the feature extraction. So then, once it goes to the global model extract the aggregation of the features only. So that means the lower layer. So basically, so here when we take the local model and the global model, we exchange in the neural network only the lower layer weights, not the full weight, because if you take the upper layer and lower together, we are going to have the huge amount of data to be transmitted. But we have limited communication resources, so that's what we consider the partial model aggregation. Partial model aggregation means in every local model, we have the features, the lower layer weight only, we update and we aggregate and we exchange. So here, so to do the experiment, these data sets are available in these 2 data sets. So here one is MNIST. So and see, these 2 data sets, it consists 50,000 training data set and 10,000 or something. 10,000 data sets for testing, 50,000 for training. These 2 are available data sets in the neural network community. So we use these 2 data sets for this partial aggregation. So then we found that, so we aggregate only the lower layer, feature extracted. So they sufficiently extract the features and perform better. So we don't need to extract all layers, only we did the partial layer. So then we quantify the computation cost and the energy consumption, computation time, and we formulated. So then we communication part. This one computation part. For computation, how much energy is taken and what is the time taken for computation. For communication, so what is the communication energy consumption? What is the time taken for communication? So then we formulated a optimization problem. So here we have to minimize the total energy taken for communication and computation with different constraints. So here we have computation time constraint, so energy constraint, so wireless resources constraint, latency constraint. With number of constraints, we have to minimize the total energy. So then we solve this optimization problem. Now, in summary, so what is the problem in federated learning? Federated learning means you have a edge server, global to prepare the global model. So local models, local devices, they have their own data set. So they have their own data set. They update their own model. Then they exchange the weight to the global server. Global server collect all weights and update and exchange to the devices. Then devices update again. So up and down. Finally, if it converges, so then the devices and global server, they come up with a global model. By this way, privacy of data is maintained, because the user devices, they do not need to transfer their old data to the cloud. So then the earlier cloud, using old data, they prepare a model and send the model there. But now, to preserve the privacy, so the training at the local model send only the weight. So that is the main purpose of federated learning, to have the privacy in the local devices. But the problem is communication and computation cost. Because why communication and computation cost? All devices, if they want to do the training again and again, energy will be consumed. So your phone battery will down quickly. Other one is, say when you have all devices, 100 of devices, when they exchange with the edge server, so you need communication resources. So if you take the resources of spectrum is limited. So then, say in your device, you have neural network. Neural network, you have several layers. So if you take several layers from the data, first one, feature extraction. Some layers extract the feature. Other one is extract the pattern. So pattern is, the feature extraction is common. So because of that, so what we are going to do, only the feature layer weights, feature layer parameters to exchange and with the edge server, and update only the feature layer. By that way, we can reduce the communication overhead. So we can formulate the problem, the energy for communication and computation, for partial model aggregation, not full model aggregation. So if you exchange the full model, then energy consumption very high, the communication channel requirement very high. So that is the problem that we have done. So, but in the recent years, there are numerous works on ongoing works in federated learning, mainly under different optimization problem. Because here we have heterogeneous requirement, different types of devices. So for certain common application maybe, but different computation facilities, high performance computing one device, other one is low performance. So because of this heterogeneous network, so this communication and computation, we are going to have difficulties. So that's what the main research works, how to optimize the communication resources and computation resources. That is a many research work that, so since I did not expect to present this one, so I haven't extracted my slides. There are too many slides, 200 slides I have, so that's what I could not do it, but I can extract the slides, the relevant slides, and send to Dr. Prabhat Sharma. He can share with you. So because I did not prepare, I did not come with the relevant slides, concise slides like other topics. Other topics I selected the slides concise way to present. Here I put everything. So, but I can take it. But I gave you rough idea in the current hot topic in machine learning. So current topic is federated learning is the current hot topic to maintain the privacy. But the problem is communication, computation resources. So you can formulate the problem like this. If you see the recent literatures, because this topic only within last 5 years, in communication community within last 3 years. So, so the main idea is to formulate the optimization problem and how to solve the optimization problem. Okay, so I can stop now. So now you have.
There's any, I'm also working on an optimization problem. So is there any approach towards finding out the suitable optimization technique for that? I have some constraints mentioned. I'm going through those things. So is there any systematic way to cut down the thing and some conclude statement? What do you think?
Yeah, so actually most of the recent literature, they do certain assumption, approximation to make it as to transform into convex optimization problem. That's what in most recent literature.
I have seen that.
Yeah, yeah.
Except that, is there any other approach or something?
Uh, if it is non-convex problem, so in the recent works, they use the machine learning approaches. If it is non-convex, because you cannot solve using the conventional tools, because model deficit or algorithm deficit or model deficit. So then only we go for this one, machine learning.
Sir, how to start a research on physical layer with the help of machine learning?
So physical.
Is it any research problem on physical work if we want to do with machine learning?
Yeah.
How to start
Machine learning
on the physical layer?
Physical layer. Physical layer problem.
Yeah, like basic outage, capacity, bit rate, throughput, and if we want to apply or predict these.
So machine learning in physical layer, so many issues, they formulate the problem.
Immediately, I have seen the papers that only deep learning evaluation is there. For the physical layer,
Yeah. To physical layer, which problem? There are many problems, resource allocation problem. They use the machine learning. So they formulated the what is the objective function, what you are going to achieve with certain constant. Then you select appropriate machine learning algorithm. Then you are going to see what are the stage, what are the same is very important learning. In some cases, they use the voice learning like no prediction and other things. So whether you are going to take like using voice learning or any other suitable learning, it depends on the specific application.
and sir, if we, I think you are familiar with IRS or Star IRS, Noma. Can you tell us some any problem which we can done with the help, which we can do with the help of machine learning or deep learning algorithms? Any hot problem that is not still not covered in the literature?
So the channel estimation.
Channel estimation.
Yeah. So that the significant breakthrough or anything, because here in just consider reflection, in addition to the reflection, they consider the transmission.
Yes.
So the main thing you are going to have a composite channel.
Yes, sir.
So because it is difficult to estimate in server, you are going to have passive elements. So the problem is estimating the compound channel.
At the base station.
Yeah.
Is there any other model that's for outage prediction in the physical layer, or maybe any parameter prediction without using deep learning? Is there any else with the help of reinforcement learning or with machine learning we can do? Because I have seen many papers, deep learning models are there for prediction purpose.
Yeah.
So I have not seen any reinforcement learning or any predictive learning or this machine learning mainly. So the allocation problems are different one in which we can use, but Is it that only deep learning is used for prediction?
No, say several different having use of different prediction applications. I have over every year hundreds of papers are coming.
Recent papers in which deep learning.
I have seen last ICT go from there for no to get an idea, I don't have to take the recent format works. So I haven't seen any ICC 2022 work on 2022 papers. Still, I have not seen. So you have seen any recent good papers only. You will be able to find the current research direction and
Generally, we cannot predict any current of research. Generally, if a recent journal paper is there, we can also have some idea. We can also take idea from that.
yeah, because you get the PDF paper, you can find. So whatever was for the program is for the current optimization for it. You can identify it. So maybe one program may not be correct. So you can find whatever real requirement, accordingly you can follow the program.
Thank you.